capacitor in AC circuit. When a capacitor is connected to an AC source and as the interest voltage continually varies in magnitude and direction, electrons must be continually passing in and out of the condenser to maintain its place at the correct potential difference. The continual charging and discharging of the condenser constitutes the AC current. Any physical quantity which possesses both magnitude and direction is called a vector. Vectors may be represented on the medium by means of straight lines or arrowheads. The length of the line indicates the magnitude of the quantity. The direction of the line and arrowhead indicates the direction in which the vector is operating. The relationship between various voltages and currents may very well be illustrated by vector diagrams. The current flow through the resistor is in phase with the voltage variation. Ohm's law is still valid to show that the current, when a resistor is connected to AC supply, sine wave, voltage represents by ERMS or simply E. Current is represented by IRMS or I. This relationship between voltage and current can be shown by the vector representation. Refer figure. The current is said to be in phase with the voltage. When a condenser is connected to AC supply of voltage ERMS, current flows in the circuit. An opposition similar to the effect like resistance in limiting the current will be seen, and we call this as capacitive reactance XC. In circuit with pure capacitance, the current follows a cosine waveform, whereas the applied voltage has a sine waveform. This is the same as a sine wave advanced by 90 degrees in phase, and it is said that the current leads the applied voltage by 90 degrees. This is shown by the vector diagram in figure. The reference vector is always taken as the current vector, which in this case of pure capacitance leads the applied voltage by 90 degrees. The capacitive reactance XC is equal to 1 over omega C, which is equal to 1 over 2 pi Fc. The unit of capacitive reactance is also ohms. Resistance and capacitance in series. if we take up a circuit with a resistance R and capacitance C connected in series and that are connected to AC supply of sine waveform as shown in figure, the flow of circuit current I through the resistor causes a voltage drop ER, which is equal to I into R, and that through the capacitor establishes a voltage drop EC. EC is equal to I into XC, where XC is the capacitive reactance. The current I should be shown by the reference vector. The voltage drop across the resistance ER is equal to I into R will be of the same phase as the current. The circuit current will be leading the voltage across the capacitor. EC is equal to I into XC by 90 degrees. The current vector is distinguished by solid arrow head. It may be to any convenient scale since there is no connection between the voltage and current scale. Since R is purely resistive, ER is equal to I into R must be in phase with the current. But the current through the capacitor must lead the voltage drop by 90 degrees. This is shown by the vector diagram in figure, where the direction of current vector is taken as the starting point. ER equal to I into R is drawn in phase with the current and of length equal to the voltage drop on any convenient scale. EC is equal to I into XC is drawn so that the current leads the voltage across the capacitor by 90 degrees. The resultant of the two voltages are not the arithmetical sum, but it is the vector sum and is determined by computing the parallelogram. Thus, the resultant, which is the supply voltage E, is the vector sum of the voltage drop across the resistance and capacitance. It will be seen that the current I leads the supply voltage E by an angle where the combined opposition put forth by the resistance and capacitance is designated as impedance Z of the circuit and can be shown by the expression the impedance Z is a complex quantity, that is to say, it has a real part R and an imaginary part XC at 90 degrees to R. The absolute magnitude of Z has already been shown.